So thanks for staying through till the last session. So I will talk about exascale for grand challenge problems in science and engineering. And the outline of the talk is fourfold. I don't know where that's coming from. The main thing I'm going to talk is about exascale in context, what it is, and then the grand challenge problems in materials and chemistry, and essentially try to at least give you enough of an indicator that we can use the exascale very effectively in the field of material science and engineering. And then connecting the dots is what I would call the last part. So essentially the talk is twofold. The aim of the talk, first is to tell you that materials and chemistry are going to be most important, one of the most important aspects of the economy going forward. And second is computing will play a key role. And how can exascale computing play a role which is different than just computing at a different flops. So let me kind of try to start off with quotes. So this is written by both Republicans and Democrats. So I thought this will be a good quote to start with. That the computers, they call it supercomputing, the key to America's innovation. I think almost all the people here would have read it. If not, it says, help design new materials, root out fraud and consumer transactions and other innovations. So this is written by political people on both sides of the spectrum. Now, in another related article, I just want everybody to get an idea that the bills have support in both parties, and there's a bipartisan House Science and National Labs Caucus, as known by the people attending this, and the federal funding is almost looks like a surety going into supercomputing. So that is a good part of the news. So exascale being, computer science is not the main field I work on. I just try to put things in numbers to tell that exascale is something that is already there. If you look at number of bytes that are consumed, we are at the zettabytes level. So that's 10 to the power 21, far higher than exabytes. But if you were to look a little bit more differently, exascale is about 1 times 10 to the power 18. The human brain connection is about 500 trillion to 1 quadrillion. That is 10 to the power 14 to 10 to the power 15. That's a connection we all carry in our heads and operate around 20 watts. Okay, so in terms of the efficiency of the wiring and the computing. Now, if you were to look into either a gram mole or number of silicon atoms in cubic centimeters, depending on who you talk to, people would argue that the silicon atoms vibrating in 1 cubic centimeter, that would be 1 microprocessor, is about more than zettabytes, right? You are talking about 50,000 quintillion number of silicon atoms vibrating. So that number is something that nature uses routinely, at least close to that number. And if you look at the world energy consumption per year, that's about 475 exajoules. So the exascale number is not that far out if you put it in the context of the other things that we work with. So now I'm going to talk about materials, chemistry, and biology and try to make a case that this is very important to the US economy. Before I do that, I wanted to define 2 things. On the left side is computational chemistry, which is to synthesize specific molecules, either organic or inorganic. On the right side is computational design of materials with targeted properties. Both are efforts which are part of a lot of national initiatives. So I want to use 3 of the announcements and quotes from different articles to kind of make a point for materials. So this is from the US Department of Energy, Computational Material Science and Chemistry. and I give the reference here, but the key thing I wanted to show was one of the things in the summary is the new materials and processes are critical pacing elements for progress in advanced energy systems and all technologies. And if you look at how they define industrial competitiveness, the company or nation with the best environment for discovering and deploying new materials and chemical processes will be the ones which are more competitive going into the future. So this is coming from one of the Department of Energy rights. And if you look at the effect on GDP, these transformational advances will create new industries and force the evolution of others. Some of you may or may not know the numbers, but if you look at US GDP, a significant fraction of that is in materials manufacture and processes. So it's a very big part of the economy as well. In 2011, the President Obama had an initiative. He was trying to borrow some of the concepts from Moore's law and tried to say that the materials should be deployed faster. I think most of you in the labs probably know about this, or universities, that the so-called materials genome initiative, that he essentially wanted to be done faster. So then, where do computing come in? And in order to understand that, we just need to take a step back and look at the overall material flow. So how are materials made and what are the applications? So I took an older edition of this because I could not find it anywhere. This is a National Academy of Sciences report from 1974, and I modified it. So raw materials are taken from the crust mostly. Mining, drilling, and harvesting, that's how you get the raw materials out. Then extrusion and refining is done on the materials to get wafers, metals, chemicals, cement, paper, and fibers, which are organic. Then synthesis and processing is done on them to get crystals, alloys, ceramics, and plastics. And then you do assembly and manufacturing, which could be structural, like the bridge, or it could be the LED, or it could be the smart glass on your iPhone, or it could be the solar panels. All these are made, this process. After it is done, they are wasted, and there are two components to it. If they are not recycled, they are disposed of. So this is the cycle for materials. So if you look at this cycle, the point I want to make is materials have a much larger cycle and a much bigger effect on the ecology of our system. But there is value added in one being able to make any of these processes efficient and faster to the market, not just in the last step. And given that I have been in the industry for a long time, I just wanted to show you some of the work that was done over 20 years. We have worked all the way from at the angstrom level, at the quantum level, into material structures and polymers, and essentially looking at micron level dimensions materials, and even looking at millimeter and the entire chip, which is the picture I put. All these pictures were taken from the work that we actually had done. So the point is, it could be done in principle. I mean, it takes a lot of work. And this article, some of this work is covered in a science article a couple of years back, and I'm kind of showing the reference. So the point here to make is technology scaling is enabled by new materials, and science and engineering are coming together via computational analysis. So this is from the industry that I worked in, which was on the semiconductor industry. But I have also done work with other people to show what would be the materials needs in other industries. So what is shown here is the electronic industry on the second column. The first column shows what properties or characteristics are important in that specific industry. Then the second one is in aerospace, and the third one is in energy storage, and the fourth one is in glass. And these are the people who essentially contributed to this. And if you take a step back and look at that, you will see that there is a lot of overlap between how materials, which properties are you interested in. So if you get from materials into chemical industry, this is the chemical industry's technology vision for 2020. And if you look at it, they talk about essentially the same thing, which is materials technology, process science and engineering, and chemical measurement. And in the materials technology, you will see that the prediction of properties is one of their priorities. And this is taken from their Industry Technology Vision 2020 roadmap. And now if you were to move into a different industry in the bio area, what I have taken is from an article written by Merck researchers. This is called systems pharmacology, because here the point is how would the drug be affecting a system at the system level. And you can look at it from disease models, drug models, trial models, or risk-benefit models. They can be either totally empirical, based on data, or it could be semi-empirical based on physics, chemistry, and data. And the whole thing is integrated, and Merck claims in this article that this is increasingly becoming an efficient way for them to look at opportunities to target drugs. And if you were to take a step back again, if you look at what is called a Physiome project, the intent is to look at length scales all the way to a human biome, and then going all the way into the genome on the left-hand side at the molecular level. So the protein folding is done at the molecular level, then you have the cell structure, the tissue, the organ, and that. So the point of this, trying to show you all that, is they all have commonalities. And if you were to look at a framework for a drug design, they essentially are trying to have a desired product attributes with the drug substance attributes. They are trying to link them. So in a way, the same concept of a material design. So the point of this is that it is a very important field, not just for economy side, but also from a social side. So I'm going to talk to you about a little bit of evolution of new paradigms and try to push this in where computing enters the picture. So if you look at the four paradigms, you saw it in one of the papers today morning. Data analysis is considered the fourth paradigm. The first one was experimental, then theoretical analysis, then computational, and data analysis. If you were to try to predict what would be the fifth one, it would be based on information processing and translation. So it is not just data, but it is the ability to translate information from one form to the other. And that seems like a powerful thing that is going to happen. So now, looking at it from another perspective, this is a business publication, McKinsey's 2013. They talk about potentially economically disruptive technologies, by which disruptions are when business models happen to the existing incumbent way of doing things is totally disrupted by either a different kind of a device, a different kind of a material, a different kind of a process, or a different way of doing things. And that is what is called disruption. So they identify about 12 items, and I show 10 of them that is relevant to us as the ones which are going to completely upstage the economy in US and world over in the next, by 2025. They expect that within the next 10 years, this would completely disrupt everything that we know today. So this is in 2013. Now, if you look at it from a Department of Energy perspective, this is from the scientific side. They have identified about 5 things which challenges the science, which is going to be challenging the science in the future, which is control of material processes, design perfect atom and energy efficient synthesis, emergence of remarkable properties, and then characterization and control of non-equilibrium systems, and then leverage the information from biosystems. So if you were to look at these two, on one side the economically disruptive technologies, and the other side the challenges for science and engineering, I hope you see what I'm trying to do here. If you try to distill them into commonalities, you will end up with about 5 items. I mean, you could word them differently, but these 5 items are about design, way of designing things, materials and devices, sensing, automation, and miniaturization, fabrication, and testing. So some sort of manufacturing. And if you think a little bit more into it, you can see that computing will be connecting the dots, but not computing the way we do traditional computing. And that is what I'm going to talk about in the next few slides. So if you were to go into exascale, or the other way which I'm going to say is exascale is more than just exascale. It is a way of thinking that needs to be a little different. Or I would even argue that the petascale came, and a lot of us who were users of large-scale computing didn't see the benefits. So we don't want the exascale to be something, if we are planning to use computing to solve some of the bigger grand challenge problems, the premise that I am putting forth is that we should do it a little bit differently. So how different, and what is it we should do differently? So this is the perspective that I'm going to talk about. So remember, I told you the materials design, and this is equally applicable to drug design as well. It is solving an inverse problem. I know what I want, but what is it that I should be making? Or what is the structure I need? What is the atomic configuration I need? And so on. The issue with the inverse problem is that it is unknown causes for known effects. And because of that, it is an ill-posed problem intrinsically, and there is no existence that is guaranteed. So this problem is not a straightforward computing problem. It has even an existence issue. And over the years, if you look at the kind of problems we have faced, you could bin the reason that the inverse problem is hard due to 6 different items that I have identified here. One is the ability to measure. The second is the ability to synthesize. The third is the intrinsic disparity in scales. And the fourth is the ability to compute the things you want to. And then there is complexity and combinatorics, which is associated with trying to go from a small scale to a large scale. And I will touch upon each of those very quickly in the next 5 minutes. So if you look at the scale of things, this is taken from a DOE website. On the left-hand side is all natural things. On the right-hand side, it is man-made. So one thing is clear. Almost at every level, multiple scales are put together for either nature to do something or for any of the advanced systems that we manufacture. Both of them span multiple scales because you try to exploit different scales differently. And then, based on a simple linear extrapolation type calculations that I did, what is shown on the x-axis is the number of atoms and the flops that you essentially can get at the time this plot was done. This plot was done a few years back, so it's a little outdated, but it wouldn't change the conclusion. So if I were to assume a linear scaling, in order to solve the problem that I really want to be predictive about, which is at 1 times 10 to the power 12, about 1 trillion atoms level, you can see that other than linear scaling, almost all the other scaling, even with exascale, I can't solve it. So the point I want to make is, unless all the codes, all the algorithms, everything scale linearly, even with exascale, it could be a difficult task. This is assuming the best case scenario. This is on the length scale. Now, if you were to look at time scale, if I were to do reliability testing of things that we do, I need to be able to test things up to 24 hours, even assuming linear scaling from the previous slide. If I were to look at the time it takes to solve the problem, I would need more than exascale to actually simulate a real time scale problem for 24 hours. So this is the point trying to say that it is not just getting to the scale that is important, how you get to it is important. Now, I talked to you about combinatorial problem, which I'm going to show you now. So the number of elements that we can do from periodic table is approximately 70 that we could use in a given system. If you try to alloy it, you can have of the order of 1 million combinations possible, bulk materials which are stable. But if you were to look at inorganic structures, not the organic, just the inorganic structures, you have up to 200,000 possibilities for bulk materials. The minute I try to put two surfaces together, they enter into 1 billion possibilities. And if I go to multiple interfaces, they are in trillion type possibilities, which means there is no a priori way for me to come up with, no matter how big the throughput, how fast the throughput is, I still will not be able to go through this whole combinations of interfaces for a realistic structure with multiple surfaces on them. I also talked about complexity, so let me try to explain what this is. What is shown here is a cross-section of a chip that has been cut, and these are the metal lines that are crisscrossing for interconnection and power. And if you look at that chip, you can see that the crystal grains are arbitrarily oriented. And how would you go after this crystal structure? First, you need to characterize them to know what those structures are. So here is a technique which is a high throughput technique that was developed, in which it's hollow cone dark field microscopy, which was essentially used by one of the collaborators, and it essentially brings out the crystal orientation that is given on the bottom right. Okay. Once you get that, then you can try to simulate the different orientations and try to predict the resistivity, here the conductance of copper. The experimental data is given on the second column and the model predictions are given on the third column. The whole point of that is we are able to do it, but we had to use the metrology, which was high throughput, and then a statistical variation on the computing that we could do. Now, if you were to look into the the metabolic pathways are very complicated, and more than complicated. First of all, they're complicated to even understand, but in addition, they're also complex because the combinations are far more than you could essentially estimate it by computing. If you look at the disease network, this is work that was taken from the National Academy of Sciences. You can see that the human disease network is pretty complex as well. So no matter which specific application you look, there is this combinatorial complexity trade-offs that are happening in real systems. So then where should the exascale come in? So the point I am trying to make here is on the first column, I am trying to list the different components on materials. And if I were to solve the problem by inverse design, I need to be able to address complexity, multi-scale physics, computation, data analysis, and data linking, that is, use the data. From a computer architecture, I need to deal with CPU, GPU, and FPGA, possibly, or a heterogeneous or some sort of a variable architecture. And from an algorithm, either I may have to deal with primary type solvers, which is eigenvalue solvers, matrix multipliers, or more secondary, which is more complex properties and surfaces and interfaces, or even more complicated in terms of rare events, which I need to be able to simulate. From a software, the issues are job scheduling and management, structure property loops, resilience, optimization, store memory, and communication and load balancing. All these need to be addressed. So if you were to ask, an exascale should be enabling inverse design for real applications. That would be the premise that I am trying to say. So I have heard these discussions in this meeting, so I just wanted to make this. It is not an either-or proposition about, it is more than flops. The problem at exascale in my mind, if you agree that inverse design is what we could solve, then it's more than about flops. It's more than about data analysis. It is more than data to compute or compute to data. It is a lot more involved than that. So then, the way I would summarize this is, there is a new paradigm that is arriving, which is driven by increasing needs for well-being. It's an information-based inverse design. Industrial level disruptions are coming. It is solvable and practical, given that we have done it in certain limited applications, but it could be scaled. But tremendous efforts are needed. For materials, chemistry, and biology, problem is challenging. I think I tried to make this point. There is an emergence behavior, dimensions are varying, and there are interfaces and complexity in properties. So from a computing perspective, it's not just about exascale, but the need for co-design and co-optimization for real applications, because then you are essentially affecting the bottom line for the real economy as well as the business for the exascale essentially makes a lot of things that could be solved from a societal perspective. Thank you.